videos on YouTube for this class. And I think I should probably avoid writing very close to the top. Should probably avoid writing close to the top and very close to the bottom. Maybe I should write bigger. Also, I think I noticed I looked at some of the class lectures that are on YouTube, and it seems like they have some light coming right from the top. And I guess we don't have a light coming from the top. Malaiya, we have these lights. So we were looking at test generation, and so I was mentioning about, so there are two approaches we are looking at. One is the algebraic approach, and other is the structural approach. And so right now we are looking at the structural approach, and we looked at the D notation. So D means it is a D if it is 1 normally, and 0 in presence of a fault. And D bar, of course, is just the opposite. So D bar means 0 normally and 1 in presence of the fault. And we looked at rules for propagation for D algorithm, which are basically simple, follow basic rules of algebra. And we looked at the single path propagation. And so we noticed that the important steps are, first you need to excite the fault. You need to create an error at the site of the fault. And then you need to propagate the error to the output. And then you need to do justification. And whenever appropriate, you need to do implication. That means when you choose some values, some other values get implied. And we have seen that single path propagation may fail, and we have seen an example, Schneider's counterexample. And we are looking at the D algorithm today. And basically, I had given steps for a D algorithm, and the steps include excitation, and then D drive, basically driving the D frontier forwards, and line justification. And you need to backtrack whenever needed. So during the process, at various points in time, you will make some choice. So you have, let us say, 3 choices, you pick one, and if it doesn't work, you will come back and pick the second option, and so basically keep trying. And you will try with single path propagation. If single path propagation does not work, then you will try multiple path propagation. So let us look at an example of the algorithm. And so we are going to have a diagram, and we are going to get a test for this circuit. So here is an example circuit. So here we have, the circuit is not too big. Now this example actually has been constructed to serve as a reasonably good example, in the sense that it's not too big and still gives us some way to illustrate how the whole procedure works. And I'm going to label the nodes. So these will serve as the labels. I would call them A, B, C something, but why not? I'll just use the numbers. And let me call this node 5. Notice, strictly speaking, these and these are different lines, because whenever you have a fan out, the branches are supposed to be different lines. But since we are going to be considering test generation here, that is a NOR, supposed to be a NOR gate here. I should make sure that this is exactly what I have in my notes, so that, and we are going to test for a potential stuck at one fault here. And so let me call this node 6, this node 7, this is 8, and this is node 9. So the fault is basically the output of the NOR gate, and let us say it is stuck at 1. So that is what we want to generate. But before that, let's take a look at the feedback module, your examples of redundancy. And let me mention some of the examples you guys suggested. Okay, I'm reading from your submissions here. Okay, so natural world, human beings, they possess 2 kidneys, and only one is needed, which is true. And as you know, you can donate 1 kidney and still live. Although that reduces the redundancy and hence capability of fault tolerance if you happen to lose your other one. But it is an example of redundancy. And computer related, RAID, redundant array of inexpensive disks. This is a rather simple example, but very effective example of fault tolerance in computers. And so multiple disks will not fail at the same time. And human design. Okay, emergency power system in buildings. So many buildings have a backup power system. So that's, oh, I forgot to mention. Having 2 kidneys, that is a spatial or replication type of redundancy. RAID is a spatial, which is replication of hardware redundancy. Okay, human design. You have emergency backup system. So regular power supply fails, you switch to the backup power supply, and that. Okay, is that what kind of redundancy is that? It says temporal here, which I guess is right, because once the regular supply goes out, you switch to the new one. But I suppose you could also call it spatial, because it does require extra equipment. This is actually very common in India, where light goes out often, and people have generators in shops. Okay. Okay, data redundancy, disk arrays. So, I mentioned about that example. That's a nice example of redundancy in computer systems. Okay. And, okay, we can call this information redundancy of the spatial type. That's correct, because it's spatial, extra hardware, and you do replicate data. Another is human beings. Oh, another example of kidneys. So that's, I think that's a popular example. So very effective. Okay, human design spare key. So whenever you buy a lock, you always get two keys, right? So because if you lose one, you will have the other key. And all the cars come with a spare key. So, and it is a form of hardware redundancy. And of course, it's not very expensive to have two keys. It is expensive if you lose a key and you get somebody to make you another key. That can turn out to be expensive. But if you start with having two keys, then the manufacturer getting the second key is not expensive at all. Okay. Oh, I see, another. Okay, kidneys seem to be a popular example. So I see another example of kidneys. Now there are actually many examples in the human body of redundancy of different type. Okay, computer related, inversion programming, and that has been used in some situations. And so basically you have multiple versions of the software, and if one version doesn't work, you switch to a different version. And of course, for it to work, the second version should have been designed independently. But sometimes the second version is a previous version of the software. And in fact, sometimes if you install an update of a software, and if it doesn't work for whatever reason, then sometimes you can go back to the previous version, which sort of is a version of inversion programming. But it has been used in some situations, like it has been used in some critical systems like flight control, space shuttle. There are some problems with redundant software. And as we will talk later, people have found that even if you have different people developing the programs for the same specifications, they sometimes would make the same mistakes. So that is something that we will talk about. Okay, another human design. In the nuclear power systems, emergency power system, that is similar to what one of you said. And of course, for something like nuclear power system, regarding the consequences, the cost is almost negligible. Okay. Now this, one of you submitted something in a format that I haven't quite figured out, so I haven't been quite able to read this. So this is from Homer. I guess he's not here right now. He's talking about linguistic redundancy. And in